And I'll quickly delve into Dr. Lewis' bio. Right, Dr. Lewis Montestruque is a senior consultant for Xylem USA. Lewis has a PhD degree in control systems theory from the electrical engineering department at the University of Notre Dame in Indiana, USA. He founded MNET in 2004 to focus on the optimization of wastewater networks. In 2017, MNET joined Xylem to accelerate the development and implementation of smart water applications for utilities around the world. Lewis now supports the digital solutions team in Xylem, which integrates Internet of Things, big data, and artificial intelligence to build intelligent urban water systems. Dr. Lewis, the floor is yours. Thank you very much. I think you are muted, Dr. Lewis. We can hear you. You seem to be muted.
Can you hear me now?
Yes, we can. Yes.
Excellent, excellent. Thank you so much. Thank you, Dr. Wool. So thank you, everyone, for your time today. This is a presentation on IoT and artificial intelligence and how do we apply these kind of technologies for what we call the urban water cycle. So during this presentation, I will talk a little bit about enabling technologies for managing water in general in city settings. I will talk about a framework called the Real-Time Decision Support System Framework, which is what we use to implement and utilize these technologies. And then I will take some time to talk about 3 use cases for segments of the water cycle and how these technologies get to be applied. So again, thank you very much for your time. So what we call the urban water cycle is the cycle of water in cities. And this picture shows that vision. So we have a water source. We have a intake into a drinking water treatment plant and a distribution network that then distributes water to residents and industries. And then there is a wastewater and stormwater that gets to be released. In some cases, it's the same pipe. In some other cases, they are separate systems to a wastewater treatment plant. And then that water gets to be cleaned and purified and returned back to the environment. And the idea is that we can utilize technologies to look at this water cycle in a much more comprehensive way that traditionally has been done, extracting lots of information out of it and making informed decisions that would result in an energy efficient, affordable, and resilient urban water cycle. And the way that I started in the water industry was looking at how do we utilize technologies such as IoT and artificial intelligence for a number of different applications. But one of the things that struck me as I was finishing my PhD was the daring situation that we have with respect to water. There is a world water crisis. I think it is one of the biggest challenges that we face as humanity. We can look at a number of different aspects of our lives, but without water, we find ourselves in a very precarious situation. These are some interesting numbers that I was able to collect. 74% of world's disasters are water related, usually water drought or flooding. 80% of the wastewater is released to the environment without any treatment. And this water usually is water that somewhere downstream gets to be consumed for drinking as well. So that is a gigantic problem. More than 2 billion people lack access to safe, clean water, and 68% of the world's population will live in urban areas by 2050. This means that the urban water cycle and taking care of the urban water cycle is more important than ever. This is another example that I was able to get, which is pretty dramatic. The picture that you're looking at here is of the desert of Antofagasta in Chile, which is not too far from where I grew up. And in this desert, it rains no more than 3 millimeters of rainfall per year in some locations. So it's extremely dry. It's one of the driest deserts in the world. But in 2015, this area experienced a big storm event that dumped more than 23 millimeters of water in this area over a period of 12 hours, causing 26 fatalities. So this is an example of how this climate change is affecting our day-to-day living with various extremes. And last year, there was even snow coming down on this location. So again, climate change is a big driver for be able to implement new ways of managing water. So let's take a look at some common problems that we find in the urban water cycle. One of them is water contamination, and this is observed everywhere. This picture that you see here is of a outlet that releases raw sewage into a canal in New York City during large storm events. And this area is essentially very, very toxic due to the frequent releases of raw, untreated wastewater into this area. Chronic flooding, we talked a little bit about this. This picture is from a 2017 storm flooding an area around Houston due to Storm Harvey. Again, a common problem that we find in large urban areas with large amounts of impervious surfaces. Droughts as well. I was able to gather this picture from Cape Town's Day Zero event, and this is Cape Town's largest reservoir, which was at 11% capacity in March of 2018. So all of these things affect our life, and the infrastructure that we have to be able to distribute and collect water in many cases is inadequate or lacking in general. So this is a huge problem in the world. So when we are looking at the water utility, we identify a three-part problem. We call this a trilemma. It's an issue where we experience problems where, or three-part problem. And the first one is the need for capital investment. Utilities require to invest money due to changes in demographics. For example, a new area gets to be built that they require new infrastructure for both drinking water and sanitation services. Climate change, we need to invest in drilling new wells, in building new treatment facilities, in providing infrastructure to deal with stormwater. And they need to be able to, at the same time, do this in a way that maintains those that are currently served by the water utility undisturbed. And the citizens that they serve have very stringent expectations about the water that comes out of the faucet. In some locations, regulations are such that water is regulated down to the parts per billion in some cases. So there's a risk aversion that comes as a natural way of operating for these utilities. And they need to be able to do this affordably. So they need to invest and maintain the status quo while keeping rates an affordable rate, so that the burden that is on the ratepayers is kept at bay. In many places where you have great disparities in terms of socioeconomical disparities, it is important that water is maintained and affordable for those who don't have the means to pay much for it. So looking at this trilemma, then it seems like new technologies and the status quo won't work. So this is where we think about digital solutions as a way of solving the trilemma by leveraging data and analytics to be able to unlock value out of it and be able to solve these problems. So let's take one case, the city of South Bend, Indiana. This is the city where I am currently located. It is about an hour and a half east of Chicago. It's a small city. It has about 100,000 people in it, and about 33% of the population is below the poverty line. So by no means a wealthy city. And they had a big problem that many cities around in the United States have, which is a stormwater problem. There's more than 700 cities in the United States that have a problem where the same infrastructure to convey wastewater is also used to remove stormwater from the streets. And when it rains, and when it rains hard in these cities, untreated sewage gets to be released to rivers, lakes, and oceans to avoid flooding, for example, the wastewater treatment plant. In the case of South Bend, their problem was significant. About 7.5 billion liters per year are released out of the sewers of South Bend into the St. Joseph River. So traditional solutions for this, and this was the original plan that South Bend had to solve this problem, are capital intensive. Tunnels like the one that you're looking at in the picture are a typical large infrastructure solution to dealing with this problem. The problem in this case is that traditional solutions to solve the stormwater problem in this city exceeded $1 billion. So that meant more than $10,000 for every inhabitant in the city, which is clearly unaffordable. So this is where we start considering these technologies, digital solutions to be able to solve this problem. And the framework that we use is called the Real-Time Decision Support System Framework. It leverages Internet of Things and artificial intelligence and optimization algorithms to implement a framework where we first collect data to try to understand and observe how the system has behaved in the past, where the system has been trending, and where it is currently. We use a model to be able to predict how the system will behave in the future, and would serve us as a digital twin to be able to try out strategies on a model before we implement them in reality. And then an optimization layer that allows us to try to determine what are the best action items to be able to operate better the system, to avoid overflows, to avoid flooding, to avoid leakage, to reduce energy. So these three parts feed into humans, the operator, for example, that then enacts these action items. Let's take a look at a little bit closer at these three layers. So the first layer, in this case, we call turning on the lights, and we use this this phrase because we're trying to understand how this infrastructure, which is in many cases completely underground, is behaving. This is different than, for example, managing transportation, where we can actually see roads, we can see how they are maintained, if they are crumbling down or not. A lot of this infrastructure is underground and is out of sight. And so we need to be able to have the means by which we can provide visibility and transparency over this infrastructure. The second tier is to create a digital copy or a model to be able to understand how the system will behave in the future. And then the operation part, which is where once we understand how the system is going to behave in the future, we act to be able to, for example, open and close valves, turn on and turn off pumps, to be able to better manage the infrastructure and avoid the problems that we saw before. And the enabling technologies that we have to be able to do this are the Internet of Things, which allows us to deploy large sensor networks throughout the infrastructure in large geographical areas. Artificial intelligence that enables us to build digital twins of the infrastructure, and optimization algorithms, many of them that are inspired in nature, biomimicry, where, for example, we use genetic algorithms or market-based control to be able to determine what is the best way of operating. So let's drill down into these concepts for South Bend and what we did in South Bend to deal with the situation of stormwater and the overflows that they caused. So the first step is turning on the lights. Here we have a map on the left that shows all the different locations where we were able to deploy a sensor network. The sensor network in this case consisted of a device that is mounted underneath a manhole cover that contains a battery, a radio, and a sensor that measures level or flow. And these devices, about 150 of them, are deployed on critical, hydraulically critical parts of the stormwater and wastewater network, and allows us to then provide visibility on what is happening. So with this visibility, for example, we can plot how the velocity versus level characteristics in a particular pipe and how the pipe is actually operating. And when we see that that operation deviates from what we consider to be the nominal operation of that pipe, the way that pipe should operate based on how it was originally built, then action can be taken to point operations and maintenance workers to, for example, find all sorts of obstructions that prevent that pipe from working the way that it should. And this is just in one pipe. Much more visibility over how the entire system is working is able. So this was one dashboard that was built for the city of South Bend to be able to help them visualize how the network was operating at any point in time. And to give you some reference here, this pipe called the Interceptor Pipe is the largest pipe and largest infrastructure in the stormwater and wastewater system in South Bend, Indiana. It collects water from the southern part of the city with a smaller pipe that then gets bigger and bigger as it collects more water from the city. The blue boxes here are essentially the level of the water in the pipe, and whenever we see it going pink, it means that the hydraulic grade line is going above the crown of the pipe. The green line here represents at scale the elevation of the street at that particular location. So you can see here this this pipe scale is crunched horizontally. This pipe is about 10 kilometers in length, and it is expanded vertically so that it can fit on the screen. However, what you're looking at here is it's all at scale. So the city is able to look at this dashboard and look at dozens of sensors all at once and help them understand how this particular pipe is behaving. The next step, after now that we have visibility of what the system has been doing and what it is doing right now in real time, the next step is to build a digital copy or a digital twin. And this would allow us to predict what will happen in the future. To do this, we utilize a neural network application that gets to be trained with the data that we have already collected from our sensor network. And this artificial neural network is able to collect all of this data and train itself to be able to predict what will happen in the future. And the way that we understand that this artificial neural network is trained and is now able to give us a good prediction is by comparing it to a past event. So here, as an example, I will show you how that happens. In this graph that you're looking at here, we have the flow on a particular pipe over a period of time that covered a couple of storm events, one big one and a small one that happened a few days later. And in orange, we have what the neural network application is predicting this flow will be. In this case, we have only trained the neural network with 10 storm events that happened in the past. And it doesn't do a very good job at telling us and predicting how these new storms will affect the system in the future, in replicating what actually happened here with the blue line. It does recognize when a storm happens, but it doesn't do a very good job at estimating the effect of it after that. Now, the advantage of the neural network application is that as we feed it more information, it gets to be more and more accurate. So here we gave it 12 storm events that happened in the past. Here we give it 19, and here we gave it 32 events. So here you can see that after 31 storm events that were given to the neural network, my application now is able to very accurately predict how the storm will behave in the future. And so we utilize this information then with rainfall forecasts to be able to tell us how the system will react to a particular storm event that is approaching us and be able to predict how the system will happen. And we not only take the rainfall forecast as it is, but we actually go a little bit deeper and try to understand what the probabilities are for rainfall in different areas. And with this information, then we can generate a number of different possibilities of how a storm will affect a particular area and create, using a Monte Carlo simulation, a number of different scenarios of how the flow in the pipe will behave. And with this information, we can map the areas in the city that are at higher risk of flooding, for example. Now, with this information that we have up to now, we're able to understand how the system is behaving right now and how the system will behave in the future. However, we have the ability to control how the system behaves. We have a few gates and we have a few pumps in the system that we can control. And so the question is, what is the best way of controlling this network? And so for that, we were inspired by how the stock exchange behaves, and we use biomimicry to be able to how the stock exchange behaves and use that as a framework to try to come up with a optimization algorithm. So to give you an example, we have an area in the city that is experiencing too much rainfall and is about to overflow. So this area would have a computer that essentially is attached to the sensor that is detecting that increased flows are happening in that location. And there's a software agent in this device, a software agent that essentially behaves according to some simple rules of supply and demand. And so this agent says, I need to buy more capacity downstream of this network because I'm experiencing too much flows. So this agent then connects through the network to, for example, a storage that is connected to it hydraulically downstream. And it says, I need to buy capacity. Can you sell me some capacity? So the tank that is downstream has also a computer that, according to its own supply and demand curve, say, listen, I'm half full. I can sell you capacity for $2 per liter. Now, mind you, these are not real dollars. This is these are computer agents talking, simulating a market. If this tank was fuller, it may offer its capacity at $3 per liter or at $4 per liter. And so it will change up and down the cost of this capacity based on how full it is. A treatment plant might also be experiencing high flows and is even fuller or more at capacity, and so it sells its capacity at $5 per liter. Another storage tank may have actually plenty of capacity because it hasn't experienced rainfall in that area and says, I will sell you this capacity for $1 per liter. And so valves open, pumps get to be actuated, and water gets directed to the agent that has the best offer. Now this tank might get fuller and it may start having its own price increasing, and maybe it will get to the point where our blue agent starts sending water to the first tank, and in this manner, in real time, all of these agents who are competing for capacity manage to fully utilize all the infrastructure before an overflow happens. And so the results for this system has been quite good. Since the system was commissioned, first the sensor network in 2008 and the control system with the software agents at the end of 2010, we have seen an 83% reduction in overflows. Here, the light blue line represents the rainfall that South Bend has experienced since 2005. And the bars represent the amount of overflow that the city has experienced over time. So you can see here a very sharp decrease in overflows due to the smart infrastructure that now is monitoring how the system is behaving, predicting how the system will behave, and then automatically controlling how the system behaves in order to avoid flooding and overflow. And what this has resulted in for South Bend is being able to go from a $1 billion capital infrastructure investment budget down to $500 million capital infrastructure budget, simply due to a smarter way of managing the system. Another example that we see on the other side of the network, which is the water distribution network, is water loss. And the same principles apply. In this case, I'm going to tell you about the province of Air Selangor in Malaysia, with a population of 8 million people. It's a fairly large utility that manages more than 6,000 kilometers of water mains and experiences 33% of water loss due to leaks in the system. Now, you may be surprised that for every 3 glasses of water, 1 is lost, essentially due to leaks in the system. But this is actually not a bad number. It is very, very common for utilities around the world to have this level of water loss. In some cases, this number can get up to 50, 60, 70% of water loss, where water essentially leaks in different parts of the system and completely disappears in the ground. So in this case, we utilize a similar framework. Sense, in this case, what you're looking at here is a picture of a fire hydrant with a box that has a sensor that is connected to the hydrant. We have a cellular connection and a battery to be able to transmit, in this case, pressure and sound that a hydrophone is listening to in this pipe. And the system then uses this sound to be able to recognize when there is a leak in the system. Here's another example of a sensor device that is connected, in this case, to a large water main with an insertion point sensor that is listening in for possible leaks in the system. So for Air Selangor, about 1,600 sensors have been deployed in a number of different locations. And so these sensors then are able to pick up noise that may be coming from leaks. And this is the part where machine learning has been deployed to be able to recognize that a particular sound is not just a truck driving, for example, by, but it is from an actual leak. So the system is listening at all times, and a artificial intelligence system is listening for leaks that then get to be alerted to workers that then can go out and repair the leak. So for this system, about 2 leaks per week are detected, and it represents really the most optimal use of operations and maintenance workers to help them direct them to the specific locations where they need to repair leaks to be able to reduce the amount of non-revenue water that they're experiencing. Yet another example here, in this case for wastewater treatment plant, and at this point I'm going to take you to Cuxhaven in Germany, with a population of 400,000 people. They utilize about 8 million kilowatt hours per year to treat wastewater. And about 50% of the energy budget that they have gets to be utilized by the aeration system. The aeration system is nothing more than a system that blows little bubbles inside of the wastewater that helps microorganisms that live in the wastewater to break down the contaminants. So infusing air into this water is very expensive in terms of energy. And even as you can see from the picture, the majority of this air gets to be lost to the atmosphere. Only 24% of it gets to actually be used by the bacteria in the water to be able to break down the waste. And in many cases, the measurement that is being taken to understand if there's sufficient oxygen or not in the water is the dissolved oxygen, which represents less than 1%. So this is a case where we deploy a number of different water quality sensors throughout the system to understand different parameters of the water temperature, ammonia, flow in different locations, dissolved oxygen, to try to understand how the system is behaving, all with the idea that we want to be able to introduce the right amount of oxygen in the water, and we don't want to introduce more than what is actually needed by the bacteria because it is just wasted. So similarly, we utilize an artificial neural network that essentially replicates how this wastewater treatment plant behaves, and is able to give us a glimpse of what output we might get if we set aeration at a particular point. And it, just like before, the more data that we give it, the more accurate it becomes. This is a graph of the ammonium in the bioreactor and how it behaves against the blue line, which is the neural network. And so we're able to predict quite well how this system will behave. And so what we do at this point in time is we use, again, biomimicry. In this case, genetic algorithms, where we simulate thousands of different scenarios of how much oxygen is pushed into the water, as well as other parameters like how much recirculation happens within these tanks. And with this information, then we are able to select automatically what is the best solution that gives us the least amount of power consumption. So for this scenario, the key performance indicator is the amount of energy that we utilize per kilogram of waste that comes in the wastewater. And before the optimization, you can see the amount of energy, the specific energy that is used, jumps all over the place. And after the optimization, because we're able to better predict how the system will behave in the future, we're able to act proactively and be able to better control how we are utilizing the aerators to reduce the waste. And that results on eliminating all of these peaks that you're looking at that happen on the specific energy, resulting in an overall 26% of energy reduction. So real-time decision support system provides us with a framework that we can utilize effectively to be able to eliminate or mitigate all the issues that we saw on the trilemma of a water utility. Much work needs to be done still to be able to connect these systems together to be able to have a more comprehensive view of that urban water cycle. Right now, we have very advanced systems that are looking at particular segments of the water cycle, but we want to be able to, for example, understand how the wastewater network operates in such a way that we also help the wastewater treatment plant reduce the amount of energy that it uses. Going further, we want to be able to understand how water gets to be distributed throughout the entire system and how it gets to be utilized so that we can reduce the energy footprint of our drinking water network. That is something that we haven't talked about. The water in the water drinking network needs to be pushed and maintain a certain pressure and stored in different locations. That can represent a huge energy budget for energy expense for these utilities. How do we connect all of these assets in a way that we can look at them as one system and be able to better manage it? So that is the stuff that we are working and we're expecting the next generations to be looking at much more closely. Thank you very much for spending time with me talking about or looking at these systems. I welcome your questions, please. Thank you.
Okay, thank you very much, Dr. Luis Montestruque, for your very, very insightful presentation. Very exciting presentation, right? For me, I think the reason why it stands out for me is that it deploys the whole gamut of tools, right, in the smart or emerging technologies domain. There's IoT sensors, wireless sensor networks, there's IoT, there is machine learning, there is optimization, right? Embedding all those technologies. And then also in terms of analytics, you have diagnostic analytics, that's what happened. You have predictive, what is going to happen. And you have prescriptive optimization, what's going to happen. So I think it's a very, very exciting body of work. So
thank you.
I'm sure we would have questions. So I'd like to invite colleagues, students here, questions. Please just raise up your hand. No, please don't unmute your mics yet. Let's.
And Willie, you're muted.
Hello, can you hear me? I think everyone else is muted.
Can you? Okay. Can you hear me now?
Yes, I can. Thank you.
Okay. No, I think I was muted too. So I know. I think we have. I have two hands here. We have first of all Royston, and then I have Professor Rudolph that have questions. So Royston, please go first, and then Prof. Rudolph goes next.
Thank you, Dr. Montestruque, for your insightful presentation. It was very, very cool. I'm working on a similar project this year. I just wanted to ask you with regards to the energy consumption in Cruxhaven, Germany. You said they're using 50% of their allotted energy. Is that for the whole city or just for that specific section of actually purifying the water with the bubbles?
The 50% is just for the radar system. It is not for the rest of the system. So 50% of the energy budget for this utility, which manages wastewater, is utilized by the aeration system, and that's pretty common. We have seen, if you look at a utility that is looking at both wastewater and drinking water, and this is a rule of thumb, it's, you know, there's lots of exceptions, of course, but of the overall budget for a utility, about 50% gets to be utilized for the distribution system, to move water and store water. The other 50% gets to be used by the wastewater system, and out of that 50%, half of it is used by just aeration. So if you look at the overall energy budget for the urban water cycle, about 25% of it gets to be utilized for aeration. Hopefully that makes sense.
Very interesting. Yeah. Thank you. Thank you.
Thank you.
Professor Rudolph, please.
Thank you for your presentation. I did come in a little late, but I think I got the crux of it. In a city like Johannesburg, which is dealing with huge infrastructural basic problems, replacing water pipes because of the age and a lot of leakage. My question is, in terms of the application of IoT and other technologies, do you have a recommendation for a city like Johannesburg of utilizing their limited budget? In other words, would there be priorities that you would recommend, because there's no way that we could apply all the systems that you've mentioned to maximize efficiency? So yeah, my question is, what would the priorities, and with limited budgets, how would you recommend a city like Johannesburg could start the process of achieving what you have highlighted and shown?
Thank you for the question. That's a really good one. It depends on the problem. Usually, what we find is a combination of both existing infrastructure that is old and needs to be replaced, and this may not be operating as designed, and the need to expand the existing infrastructure to be able to serve other populations that are underserved, or expansion areas that we might be seeing. And all of this in the framework of a lack of budget and a lack of understanding about how the actual system, how the current system is actually operating. And that's the kind of situation where these kind of technologies really thrive. What I would recommend is getting started with understanding what is the biggest problem and utilizing small section areas of the city that are poorly understood, or they have infrastructure that is older, to be able to create a digital twin, and then using that digital twin, be able to do a couple of things. One of them is to utilize the digital twin to better understand how the system can be expanded in a much more efficient way. The digital twin enables us to run thousands of simulations in the cloud with different ways of implementing the infrastructure. We can design an area to be expanded with a pump station in location A, 2 pump stations in locations X and Y, a number of different permutations that allows us to find what is the best, most optimal capital use of infrastructure. And then the second part is utilizing the information about how the current system is working and feeding that into a digital twin that considers also the probability of failure as well as the consequence of failure, and identify specifically the areas of the system that need to be maintained because they represent a high probability of failure and a high consequence of failure that could result in an economic loss that is greater than the repair works that might need to be performed. And just to give you even more on this direction, the way that we started with South Bend, which was the first system where this system was started with a pilot back in 2004, was through a partnership between the University of Notre Dame, the city, and MNet at that time. And the combination of the three with a multidisciplinary team was able to develop then a project that included a number of different research topics to be able to utilize these technologies to solve the problem. It was only after a proof of concept was developed in a small area of the city that then the city realized that this could be beneficial for them, and the system was expanded later in 2008. So great question and great opportunities as well.
Thank you very much for your very practical response. Thanks.
Thank you.
Thank you very much, Professor Suvendi. Prof. Suvendi, can you ask a question, please? We are not. I don't think
we also have some questions on the chat.
Yes, no, we can't hear you, Prof. Suvendi. But let's just go through the questions in the chat. Then Dr. Lewis can provide a response, whilst we hope to hear you shortly. The first question is from Priscilla. It says, "Thank you, Prof, for an insightful presentation. Do you have any projects in future in developing countries in Africa, considering many aspects in wastewater effluent quality, as in pollutants, considering pollutants, basically in wastewater?"
Yes, that's a great question. Thank you, Priscilla. Africa represents a region of the world that has a number of different problems in the urban water cycle. Wastewater and the treatment of wastewater to be able to protect waterways and water bodies is definitely one of them. To be able to distribute clean, potable water to underserved communities is another big challenge that we are aware need to be more effectively addressed. We are working with a number of different utilities to try to implement these kind of projects. At the moment, more focus on the water distribution side of things and be able to help utilities be able to distribute water with as few losses in the system as possible. But with respect to wastewater, that's also a challenge that we're looking at as some utilities are developing their treatment technologies to be able to treat wastewater. Thank you.
And thank you very much, Dr. Lewis. The next question from says, "Hi, what kind of modeling systems were used for building the decision support systems? Can you please elaborate a bit more?"
Thank you. Thank you for the question. So the modeling component, as you may remember, is a part that helps us predict what will happen in the future. And there are different models for different kinds of applications. So I'm just going to give you one example. For example, for the wastewater application, we utilize a hybrid model. It's called a model that uses first principles, a physics-based model that essentially models what happens on each pipe. This hydraulic model helps us understand how the system behaves. However, we need to introduce into this model a number of different parameters that bring a lot of uncertainty. For example, one of the classic parameters that is has huge uncertainty on it is how much of the surface is permeable. So how much of the area where we experience rains has grass versus pavement, for example. And that will affect the amount of runoff that we will experience and therefore the amount of flooding that then will happen later on. And it's very difficult to understand if how much water would this area be able to absorb. So to be able to understand this and be able to model this thing better, we utilize a data-driven model as opposed to a physics-based model. On the data-driven model, we feed this model with past information and the model then is able to replicate how the system will behave in the future. And the ones that we're using these days very successful, and the one that has produced great results, are neural network applications. And in particular, neural network applications that have memory. So long short-term memory is a technology, for example, LSTM, that allows us to have a neural network that remembers what happens in the past. And that is helpful so that we can understand that, for example, it rained yesterday and the area around us is saturated, the soil is saturated, and therefore it won't be able to absorb that much water, versus it hasn't rained in a week and the soil is just going to wick away the rain as it falls. So we tailor our model to the particular problem that we're looking at, and that is just one example. And we utilize the best of both worlds, the first principles model combined with data models. Hopefully that answers the question.
Oh, thank you very much, Dr. Lewis. The next question is, you say that 33% is a good percentage of water loss due to leakages in the big city. What is the global average, and what would be a bad example of water leakage, if you know one?
So 33% is a lot of water loss. It is, but it is not bad. I wouldn't say it's good, but I wouldn't say it's bad either, or I wouldn't say it's good. I would definitely say it's a lot of water loss. There are utilities that have accomplished water reductions in the order of 15% by really focusing on the water loss component of their system. I would call that great. I would call that a great score. However, we have seen utilities that lost in the order of 50% or 60%. So it really depends on the amount of focus that the utility, and capital, of course, the utility has to be able to devote to water leakage. I wouldn't be able to tell you what the average is worldwide, but I can say that 33% water loss is more than normal. I've seen a lot of utilities in that range.
Thank you very much, Dr. Lewis. Yeah, the last question we have is by Professor Suvendi, and it says the digital twin model is good for existing infrastructure. How do we cater for South Africa, which is a semi-arid country, and population moving to urban centers with limited existing infrastructure? How do you generate the predictive AI models?
Great question. Great question. That is certainly a big problem, because as you would recognize, the digital twin, and specifically data-driven models, utilize past information to be able to model what will happen in the future. But if we don't have past information, meaning we have infrastructure that hasn't been built yet, then we don't have the ability to predict what will happen in the future. However, again, that's where hybrid models come into play in a very good way. And that allows us then to build the parts that are already built, where we actually do have data, to build a very good model representation of what is happening with the built infrastructure, and then use first principle models to go beyond that and understand how the system will behave in other places that will be built. And because they haven't been built, there may be less uncertainty over which areas are going to be permeable, which areas are not going to be permeable, what material the pipe in the distribution system is going to utilize, what kind of water loss should we expect of a system, and utilize those as design parameters then to decide how we build infrastructure. So the combination again of both of them, I think, can be really, really powerful to help us iterate over several designs that can help us find what is the most optimal one.
Thank you very much, Dr. Lewis. As a follow-up to that question, conceivably you could implement your real-time system with getting sensors and feeding it to the machine learning model, neural network model, right? Is
Yes.
the digital twin model very important, or can it be skipped in the whole process and you will still be able to use your sensors, IoT, you move it to the machine learning, and then you perform optimization? Would you still get reduction or optimized performance?
If you would help me understand a little bit the two scenarios again. One of them is feeding the sensor data to the machine learning.
Now I'm saying now that you have in your framework for your real-time support system, right? You have sensors, right, that you get. That's like the first stage. Then after, from the sensors, you get data that you now utilize in your digital twin model, which you now feed into your neural network. So I was thinking that you could deploy that system without necessarily using the digital twin. That is, you just get your sensors and you get data, right? And then you use that data to train your neural network model. And then you now get the optimal flow or whatever, and then you now optimize. So I'm just thinking that will the system still perform efficiently without necessarily having a digital twin?
Yes, the short answer is yes. I think there are many situations, and we have confronted these situations where we don't have information about how the system is set up, for example. And so all what we have is just the data, and we don't have anything else. And there is a number of different scenarios where we need to be able to make control decisions based just on the data that we have. The only caveat that I would say with that is that, and one really good technology to be able to implement this is reinforced learning systems, where you allow the system to control the application, and then it learns from that control what the best outcomes are. And the only caveat with that situation is that as it is learning how to make decisions, it might make decisions that are not particularly good all the time. But it is absolutely possible. Absolutely, yes.
Thank you very much, Dr. Lewis. And then I have another question, right? In the South Bend case, you mentioned that you deployed 150 sensors at hydrologically critical places. I think that's the phrase you used. And so I wanted to understand better what criteria, right, did you use to determine the choice of sensors, not just for the South Bend case, but for the other cases you use? Because I would imagine that there must have been maybe some optimization about the choice of 150, for instance, or and then that would also have some economic implications. So what criteria did you use for that? And then for the other case studies in the choice, I think you had the hydrant in the other case in Germany. What are the factors that you use in choosing your sensor locations?
That is a great question. So in control system theory, there is a concept of observability comes to mind when we're looking at this. But in many cases, the utility itself wants to see more into their system. In essence, there's a minimum number of sensors that need to be deployed to be able to control the system. And then you can provide the utility with more visibility after that. But how do we determine what are the actual control sites that need to be measured are determined by the control strategy. So in the example of South Bend, you saw that we had agents, and these agents are determining what control action needs to be taken by bidding in the sewer capacity. And so we have control agents. Those are locations where we actually need to have infrastructure. But then there is the locations where we may have an overflow, which is something that we want to measure. And then there are locations that are able to bid for, they're able to sell capacity. So tanks, wastewater treatment plants, all of those need to have sensors. And then finally, in between a seller and a buyer, we may have a constraint in hydraulically in the system. And so we will select those constraints to have sensors on them as well, so that they can provide information about constraints in the optimization problem.
That's nice. Thank you very much, Dr. Lewis. I think
Absolutely.
I just have 2 more questions, and I think okay. No, I see Professor Suventi has a question, and it says, "Is there a shared database where we can look for similar climate and infrastructure conditions, which can inform what infrastructure is newly built?" So, in other words, using digital twins data to inform our models. I think that's what I understand it to be. Is there like a shared database maybe that we could use for maybe water infrastructure, right? And then we can now maybe extrapolate informations in terms of similarity of climate and then water needs in informing the kind of infrastructure we can build.
Not that I'm aware of, and that is an excellent idea.
Thank you. Then I think finally, let me ask 2 questions in one. The first one has to do with your neural network model. You said, I think that you used 12 storm events, if I'm not mistaken, in the South Bend case, I think. So I was wondering what are the storm events? Is that like a set of other parameters? When you say storm events, what does it actually mean?
Yeah, so a storm event, we would pick, normally the way that we do things is we look at the last year of events, and we utilize out of that year, we utilize all the storm events that happened during that year to feed into our neural network application. We do that regularly. And the reason for that is there's always changes in the infrastructure. These systems normally experience changes because they are building a new area, or because a pipe became blocked, or is under maintenance, or there's some other area that is under construction. And so there are changes on the system that need to be updated on a regular fashion. And the hope is that if we cover the last year worth of data, we would have enough variety of small storm events with a recurrence rate of 3 months, as well as a few storm events that would have large storm events that will have maybe a recurrence of once every year or every 5 years. We would also like to introduce sometimes larger storm events that happen in the past to train our neural network to be able to deal or cope with situations where we have an oversized storm event, like a 10-year or a 50-year storm event, which these days are happening more frequently than 10 years or 50 years. But the point is, we want to have a variety of different storm events. The example that I gave was just to show how is it that we get asymptotically close to a perfect prediction the more information that we're given this network application.
Well, thank you. And then finally, my last question, and I'm not asking anymore. I know most control system guys, they prefer classical optimization methods, basically. Yeah, but I see that you're leveraging some bit of GA, right? So I wanted to know what informed that, or GA or other biomimicry-based optimization approaches, right? So I wanted to know what informed that choice. Are you also guaranteed like maybe a global optimum using such approaches, or do you just want to use bio-inspired algorithms?
That is a great question. So there's several aspects to this. One of them is this in the case of the wastewater and stormwater applications, these systems are highly nonlinear. We have overflows. We have hysteresis at pump stations. We have all sorts of delays on the system, and so controlling it with, more traditional control system methodologies can become very, very, very difficult. Because we cannot build a linear model out of this. And so on one hand, we have the situation where we may have a highly nonlinear system with a problem that in many cases is not convex, and where we may have even a bunch of different local minima. So that's on one hand that pushed us in the direction to more heuristical methods like genetic algorithms or this market-based optimization. For very, very simple cases where we can build a linear model, you can show that the model-based control, for example, does render the optimal solution. But in the real world, that's a lot more difficult to do. The other aspect that affected the decision here was actually trying to make the technology more easily understood by those who are owning the system at the end. And so trying to explain the market-based optimization results on something that is a lot simpler to explain to a wastewater treatment plant operator than, let's say, an LQR controller. So that on itself, it was a big driver to be able to get us to this kind of control system. The literature is full of examples that utilize mixed integer programming techniques, for example, in the case of the wastewater. But like I was mentioning, this is a very, very reluctant industry to adopting technologies. And so these people need to understand a way of operating the system. In a way, it reminds me a lot of the benefits that fuzzy logic, for example, brought to the table. A lot of operators do understand how the system behaves, and being able to infuse their knowledge into the systems became a lot easier with fuzzy logic. Market-based control accomplished something similar in that regard.
Okay, and then any instance of MPC model predictive control in any of your solutions?
Yes. So model predictive control again is a technology that we utilize sparsely when we find the right conditions. A typical example that we'd like to utilize NPC is when dealing with large tanks that are easier to model and where we cannot determine a control strategy without understanding how it's going to affect in the future. So that is a typical scenario where NPC is very, very well advised to use.
Wow. Okay, no, thank you. I don't have any further questions again. No, but and I don't think anyone in the audience also has. So in closing, we want to thank you so very much, Dr. Lewis. Thank you kindly for agreeing to give this talk, and then also for a very well thought out and very practical presentation. So really and truly, one is able to visualize the transition or the benefits of some of the theoretical concepts, right? Seeing them put in practical use, right? And it's very, very excellent. So thank you very much. Thank you,
Professor Willow, for inviting me. This is the highlight of my day, which is just starting here in the US.
Yeah.
Thank you very much. Thank you very much for having me.
All right, and we hope that once we invite you again, you would oblige us.
Absolutely.
All right, thank you very much, and everyone, have a lovely weekend ahead for those of us in South Africa, and do keep safe. Thank you. Bye.
Bye.